Hello everyone, welcome to the ECS workshop. I'm very impressed that all of you want to spend your Saturday basically listening to an extremely dry college lecture, but here we are. You should all pat yourselves on the back. So a little bit about me. I graduated from college in 2012. I worked on Hyper Light Drifter. I ported some indie games to some consoles. I'm a co-maintainer of the FNA game framework, which Brendan and Laura have used. And you, great. Beyond that, I maintain a suite of open source game development tools, including an ECS framework that I'll talk a little bit about, and I'm putting it into practice on Samurai Gunn 2 with Bo. We've learned a lot of lessons putting this into practice and actual production, so I'll try to share some of our hard-earned knowledge today. So the question you're all wondering about, what is ECS? You've probably heard about ECS because Unity announced like a big push for implementing ECS in their engine like 6 years ago. It's mostly been a failure, and they just fired Mike Acton like 3 days ago, so we'll see how that goes. Mike Acton, I guess ECS, the concept behind ECS has been around for quite a long time. I think people were first theorizing about it in like the early 2000s, and it got somewhat evangelized by Mike Acton. He's a big proponent of data-oriented design, which is related to ECS. ECS is like a form of data-oriented design. So he's been the big guy evangelizing data-oriented design for a long time, and he's worked at Unity since 2017, but not anymore. So we'll see how that goes. You don't need to use Unity to use ECS. But actually, before we talk about what ECS is, I think we need to ask ourselves some bigger questions first. So what is the role of a game programmer? There's a lot of different kinds of programming in the world. What is it that makes being a game programmer unique? What is it that we are actually called to do, like on a day-to-day basis? There's some obvious things, like games are real-time visual applications, so we have to focus on questions like efficient real-time performance, rendering. We have to do what most programmers do, which is translate abstract design ideas into concrete rule-based systems that function as you expect them to function. But we have another very important role on a creative team, and that is creating a foundation that everyone else can rely on. You are creating the canvas upon which every other creative member of the team is able to express themselves. So, your goal as a game programmer is to facilitate people's creative choices. And I think a lot of people think that programming is about telling people no. And I think it's about telling people yes. If someone on your team wants something, you should do everything in your power to say yes before you say no. Obviously, we're limited by technical restrictions. There's some things computers can't do, at least, not within 16 milliseconds per frame. But it's your job to do everything that you can do within those limitations. If the processes you designed or you're relying on are interfering with the output of an animator or a musician or a designer, that's your problem. It's not anybody else's problem. And I think that's a responsibility, and honestly, it's an honor that you should take very seriously, that other people are relying on you to express themselves. Unlike most kinds of programming, our programs are designed to perform kind of subjective tasks. We're trying to evoke feelings from players through play. So if you've ever worked on a game, you know that things don't really turn out the way that you expect them to when you design them up front. Like maybe a play test doesn't go very well, you need to make some tweaks. Maybe your designer comes up with a really cool idea on the spot. The point is that in this creative space, your requirements change rapidly. And above everything else, I think that you need flexibility. So that's where most problems arise when we're talking about game architecture. So what is code architecture? I hear a lot from people that coding games is uniquely difficult. I'm not really going to dispute that. I know we've all been in situations where a feature took, you thought it would take a few hours and it took a few weeks, or a bug you fixed 10 times keeps coming back. But I think a lot of the perception of implementing games being this uniquely hard problem comes from not respecting the concept of architecture and not implementing basic structural ideas and discipline. Even if you're working alone, you can do things that are nice to yourself. Like if you're the animator, like make programming choices that you enjoy working inside of as an animator, Anyway, so architecture refers to the fundamental structure of a program. So it's how new concepts are able to be added to existing programs. It's how all the different moving parts fit together. It's the foundation of everything you build. Even if you haven't thought about it very much, all programs that you write have some kind of architecture. So I'm going to talk about architecture that most of us are familiar with right now. And it goes by a lot of different names. I call it the actor model. People, call it different things. But you're probably very familiar with this concept as a game designer. It's the structural idea behind the overwhelming majority of game implementations I've ever worked in. So the actor model is a structure based on the concept of an actor. And an actor is an object that contains both data and logic. It's an obvious, intuitive idea when it comes to building, a simulation-oriented program, which is what a video game is. You think of each concept, your object in the game is a self-contained actor, and these actors can update themselves, and they can also be acted upon internally and externally via methods that that manipulate the state of the object. So, if we're talking about, 1978 asteroids, the ship is an actor, and the asteroids are actors, and the bullets the ships fire are actors. It's simple enough. And my argument is that, this is a fine structure for something that's very simple, but things aren't quite that simple once games start getting a little bit more complicated. So as programmers, we want to reuse code everywhere that we can, because every bit of duplication is an opportunity for bugs to sneak into your program. If you fix something in one place and it's duplicated, you're going to have broken behavior in other places that you're not expecting. And beyond that, repeating yourself all the time is really frustrating. It's really boring. It's a time-wasting nightmare that causes a lot of problems where you least expect. So obviously in the actor model, we have a way to reuse code, and that is inheritance. So with inheritance, you can base an object or a class partially on another class. So the inheriting class inherits all of the properties and methods of the parent, and the children of these objects can add new properties and logic as well. So if you have a ball class, it has a position and a radius property, and then you're like, oh, well, I want some balls to be able to bounce. So you create a bouncy ball class, and it adds a bounciness property, and maybe it has a bounce method. So that's simple enough, right? However, my argument is that this sucks. So inheritance has a lot of issues. It's very difficult or even impossible to mix and match behaviors from different type trees. So, if you have logic in two different kinds of types and you want to make an object that does some combination of things in both of those areas, you can't really do that without some very complicated structures. Right, another problem is that you have unexpected behavior in child objects from parent behavior. So the behavior of how children interact with their parents can be obscured because you're not seeing that code directly in the child object. So that can cause a lot of surprising things to happen. It's also really easy to inherit behavior from a class before you really think about if it makes sense for an object to behave that way, just because you're lazy. So for example, on Samurai Gunn 2, in our old version before we started using ECS, Bo implemented rolling behavior on a class called Head. So heads are created when characters get beheaded by swords and they go rolling on the ground. So originally, in early versions of the game, those were the only objects in the game that could roll. So of course we implemented that behavior on the head class. When we added other objects, like a character that can throw logs that roll, we inherited from the head class. So then when we added the feature where heads could bleed while they were rolling, now all of a sudden logs are bleeding everywhere, and that doesn't look right. You could fix stuff like that by fixing the inheritance tree. That's a lot of restructuring work, and even if you do fix it, you never know when some child object accidentally relied on some obscure part of its parent's behavior that you forgot about, and that creates bugs too. Another common mistake is to create massive God objects that huge amounts of other objects depend on for inheriting their behavior. It's really easy to make a giant mess once that pattern takes hold, but it's also easy to understand why you would build something that way, because the structure of inheritance encourages you to do that. I think on Hyperlight Drifter, the character class had like 300,000 lines of code on it or something. Like, it was insane.
Everything inherited from master.
And yes, and there's a master class that everything in the game inherited from. So it was completely insane. It was very hard to debug. Another thing I don't like is that mixing data and logic together into complicated objects encourages us to make messy designs. And we're going to talk about a concept called data logic separation in a little bit. We also run into an issue called tight coupling. This is my least favorite thing. So basically, if you have actors that reference each other's properties or methods directly, that becomes a problem if you make a change to one of them in any way. So if you have actor type B and actor type A is referencing type B, and then you change type B, now you have to change type A too, because it's depending on the structure of type B. In particularly coupled systems, you might have to modify like a dozen objects just to make a modification to the behavior of a single object. And that's our worst nightmare as game programmers. Games are very complicated. They're very complex simulation programs. So the more coupling that you have between objects, the more of the entire environment of your game you have to understand before you can pick apart how a single thing works, let alone the entire game and how everything fits together. It's really easy to surprise yourself by unexpectedly changing the behavior of multiple objects when changing one object. As programmers, we're constantly fighting a war against chaos. So you don't want surprises, except when they're cool and then you call it emergent behavior. Speaking of emergent behavior, you might think that that's something that arises out of chaotic structures, and I disagree. I think that, bugs are gonna happen no matter what you do. Like, grass grows, birds fly, software has bugs. Intentionally creating chaos because something cool might happen like 1 out of 100,000 times is not a very good idea. Like, 99,000 other times it's gonna be something that makes your head hurt. And what real emergent behavior is when you have systems that are flexible enough to accommodate unexpected but still logical rule interactions. So structuring your code to facilitate that kind of thing is a much better idea. One last note about the actor model. It can be very unclear to decide where to put behavior. Let's say that you're writing code to resolve a collision between two different object types. So where does that code live? Does one object modify the other object? Does it call a method? Does it live somewhere else? The result is that unless you're very, very disciplined, it's easy to lose track of code that's still in play and get unexpected results, or just making an organizational mess. I could probably fill a very big book about all the times I've been surprised by like weird collision interactions between two different kinds of objects. So that's enough about this way of doing things. You're all wondering what ECS is, so let's talk about that. Also, if you feel lost at all, you can interrupt me and ask a question. So yeah, just let me know. So ECS stands for Entity Component System Architecture. And entity component system architecture relies on two fundamental design principles. One of them is data logic separation. So in traditional object-oriented programming, we pay a lot of attention to a concept called encapsulation. And in encapsulation, the state of your object is partially hidden from the outside of the object, and it can only be manipulated by a set of methods that you design. So the idea is that you hide the internals because that prevents users from accidentally putting the object into an inconsistent state by manipulating it directly. So to do that, we bundle the data and the logic tightly into one object where its implementation is mostly hidden from outside of the view of the object. So ECS asks, what if that's actually not a good idea? Encapsulation leads directly to the kinds of problems that we've been talking about with inheritance, namely that the state of objects tends toward greater and greater complexity and less flexibility. The more complex objects become, the harder it is to fit new ones into the structures of our game. In ECS, data is completely separate from logic. Data is an open book. It can be manipulated by any system. And that might sound like a recipe for chaos, but it actually isn't, so we'll get into that later. Secondly, ECS implements code reuse through a concept called composition instead of inheritance. So basically, we do code reuse by composing properties and behaviors together instead of inheriting them from other objects. So you could think of this as like an is versus a has relationship. So in inheritance, you'd say, well, I want to make an apple object. So I already have a fruit object, so I'm just going to inherit from my fruit object. Now an apple is a kind of fruit. It's going to inherit a bunch of properties from fruits. With composition, you'd say, well, like, what does an apple have? Well, it's got a red peel, it has flesh, it has seeds, it has a core, it has a stem. So you would compose the apple from those different components rather than inheriting from like a tree. So the basic structure of ECS is that there are three main kinds of ideas you have to understand. So there are entities, components, and systems. An entity is basically just an ID. It doesn't have any inherent behavior, it doesn't have any properties. When you create a new entity, it does nothing. It's completely empty, it's void, and the only thing that entities do is they can have components. And what is a component? Well, it's just data. You're going to be hearing that phrase a lot from me in the next few minutes. It's literally just data. A position 2D component could have like an X and Y component to represent or an X and Y field, to represent the position of an object. Or if it was velocity, it could have a vector on it that represents, the velocity. Any kind of data that you can imagine can be represented by a component. And then what systems do is they put everything together by reading and manipulating entities and components. They can, well, I'll get into that in a second. There are some other ECS structures that are useful and are not in the handy ECS acronym, but are still very important. So a relation is just data, and it relates one entity to another entity specifically, but it also has some metadata on it. A filter is basically a set of entities that have a certain component structure. So you can use those to iterate over entities that satisfy that requirement. So that's the main thing that systems are going to do, is iterate over entities. And then a message is basically just a component that gets created and then destroyed at the end of the frame, and it's good for passing short-lived data around. So let's talk more about components. So a component is just data that is attached to an entity. And component types are unique per entity. So in most ECS systems, an entity can only have one component of each type. So you couldn't have two position components on one entity, for example. Some ECS systems disagree on this. Some will let you do multiples. I don't like it because I think it gets confusing. So what could a component represent? Well, it could represent capabilities. Things like what can the object do? So maybe our character component can attack, or it can dash. Any kind of action capability can be represented by a component. It could be properties, things like, should we blend a color with the sprite? We can represent that in a component. Maybe the entity has an ammo count. We could put that on a component as well. You can represent triggers by components. So, if an entity needs to play a sound when it dies, you can have a play sound on death component. If it needs to create sparks when a deflection happens, you can have a create sparks on deflect component. Just useful for, I'll get more into like collision later, but that's one example of that. You can have transient data on a component. So that's stuff like, if you're processing the input from your engine into like a buffer so that you can do things like, we'll let the user press a button and then still react to it like 3 frames later. You can put that on like a character entity. Or you could have like a timer that's counting down. It's like, after 10 seconds, this entity will be destroyed. You could represent that as a timer component. So just remember, it's all just data. Like if you can think about, the data structure of something that you need to represent in the game, you can probably put it on a component. And it's also important to note that components never, ever have logic. So you never want to design components in a way where they're like updating themselves every frame or like other things are acting on them directly through a method. Like, no, it's just data. If you do really, really want to put logic on your component, that is a structure called EC. It's just entity component, and you don't have systems. And I think that basically, you end up with a lot of the same problems that we were talking about earlier, with like not knowing where behavior lives, and like you end up with inheritance problems too. So we're just going to try to avoid all of that, and we're not going to put any logic on our components. The one exception to this is that it's okay to have logic on a component where you're just calculating the result of something from stuff that's already on the component. So if you were like, I want my velocity component to have like a speed magnitude, like you can calculate that from the velocity, so it would be fine to put logic on it because it's not manipulating the structure of the component in any way. But if you are manipulating the component in any way through logic on the component, that's bad. Don't do it. Systems are where the logic goes. So here's some examples of stuff that systems can do. They can check if an entity has a component of a certain type. They can check if any component of a type currently exists in the entire world. They could read data from a component off of an entity. They can add a component to an entity. They can update a component onto an entity. They can remove a component from an entity. And they can iterate over all entities that satisfy a filter. Those are the basic things that a system does. So what kinds of systems could you design? Well, you could have a velocity system. And what the velocity system is going to do is it's going to find all of the entities in your world that have a position and a velocity. And then they'll look at that and they'll add the current velocity to the position. And they'll update all of the entity positions that way. And then you can make that more abstract with like a motion system, and that's going to take, the way I like to do this is that I think motion is very tied to collision. So I like to operate on both of those things in the same system. So when you move things, you're also checking if they're colliding with things. You could have a round structure system. Like, when does the round end? When does it begin? What's happening every frame on a round? What kinds of state needs to be checked? You could do that with like a round system. You could have a respawn system. So when a character is going to respawn, you put like a timer component on something, and it's going to check those timer components. And when it ticks down to 0, then you spawn a new entity. So those are just some examples of the kinds of systems that you could design. All of your logic is going to live inside of systems. So filters are the bread and butter of systems. So a filter is basically just a set of component criteria. So it'll be like, you'll say, here's some examples from our game. So we have like an unbreakable filter. So an unbreakable entity is an entity that has a transform component. It has a solid collider, and it has an unbreakable component. That's how we know something is unbreakable. So then we can iterate over all the unbreakable objects and make sure stuff isn't breaking them. This is very important for performance. You don't need to use filters, but the problem is that filters are basically optimizations. So they will, when entities are when components are added or removed from an entity, the filters are going to update, so you don't have to be checking every single frame, every single entity, and making sure that it satisfies the criteria. It's going to cache that stuff so that it can iterate quickly over things that satisfy the criteria. So some other examples of filters from our game. We've got the can be damaged filter. So if something has a position and a can be damaged component, then we know that it can be damaged. Sweep movement is for stuff that needs to not penetrate solid objects on a single frame. So if it has a transform, a velocity, a solid collider, a use sweep movement component, and it does not have a freeze component, then we're going to execute sweep movement on those entities. So the exclude is fun because that means that, like when we want something to stop moving for a few frames, we can just put a freeze component on it, and now it's not going to be iterated on by the sweep movement filter as long as that component exists on that entity. And filters can also execute callbacks when stuff is added or removed. So one reason that's important is if you're doing collision detection, you usually have some kind of structure, like a spatial hash or something, and updating every single entity with all of the spatial hash data every single frame is really slow. So you would only want to do that when something is actually created that needs to be put in the spatial hash or needs to be removed from it, so you can do callbacks that way. Relations. A relation, like a component, is just data. However, it also defines a one-way relationship between entities. So for example, if we have an abstract player entity, players are controlling a character in the game. So you could define that relationship with a relation. A player is controlling character entity. Now, unlike components, an entity can be related to many other entities via a single relationship type. So you could even have it so a player is controlling multiple entities in the game. You could have, in our game, we use it to represent the fact that a character can have multiple hitboxes that overlap. And so the nice thing about relations is that if you can't cleanly model something with a one-to-one relationship, which is what an entity and component data is, you can usually model it with a relation instead. You just have an abstract relationship between two entity types. And you can also iterate over incoming or outgoing relations on any entity. So if we get a player entity, we can say, hey, give me all of the entities that you're controlling right now, and you'll be able to iterate over all of those. Finally, there's messages. Again, it's just data. Systems can send and read messages. They're one-directional. You can't send them back in time. So if a system is already run, you're not going to be able to read any messages that are sent after that system is run. But it's useful for triggering behavior that's going to be handled by separate systems. This is a good code reuse structure. So for example, if multiple different systems need to be able to start a round, you can have a round start message, and then the round start system is going to process that. Or destroying the HUD, playing sound effects, those are things that are good for messages. Just firing a one-off situation that doesn't need to live for a long time. You can also associate a message with a specific entity. So in our game, players, for every player, we send an input message, and the input message is associated specifically with that player entity, so we know what buttons the player pressed on that frame. We can read that from any system that we want. Isn't this basically a relational database? Yeah, you're a nerd. If you've ever done web design, this probably all sounds really familiar. This basically is a relational database. The only difference is that relational databases are optimized for different things. I actually did try to use a relational database as ECS storage once. It was really slow, 2 frames per second slow, so don't do it. Those things are designed to optimize for disk access and stuff, so don't do it. So this has been really abstract, so I'm just going to show you a system in our game. That's pretty hard to read. We'll do our best. So every frame our system runs an update method, and so we have that first line up there. If some stop action. So stop action is a component, And we're checking if some stop action component lives in the world. So in our game, we have a lot of like screen freeze effects where we don't want anything to move. So for a lot of our systems, we will pause their execution if the stop action component exists. So this is a really nice way to do time dilation because everything is so separated. You don't have to worry about like, oh, I need to make sure every single object in my game is respecting time dilation. No, it's automatically happening because anything that needs to update the position of stuff is running in the system. And you can just check if the time dilation is in the system. So basically, if we have a stop action component, we don't want to update the shake. Oh, I didn't even talk about which system this is. So this is a shake system. So basically in our game, if a character falls for a long distance and then they hit the ground, we want them to shake back and forth a little bit as kind of like a hit reaction. So it's just like a nice little effect. But we don't want the shake to actually affect the gameplay position of the sprite. We want that to stay the same. We just want the sprite, when it's rendered, to just shake back and forth a little bit. It's like a nice visual effect. So for something that's shaking, we put a shake component on it. So we are iterating over our shake filter, and the first thing we're going to do is we're going to get the shake data out of our entity that's shaking. And that shake data has an offset value. So what we're going to do in the renderer is we're going to take that offset value and we're going to add it to the gameplay position. And that way we can shake the sprite back and forth without actually changing its, like where its hitboxes and stuff like that. So we're also going to read a message called a delta time message. So this is how we do the time dilation effects in our games. Like if the game is like running in slow motion for a few frames as a visual effect, that means we're just slowing down the delta time. So we'll take the dilated delta time. Then we have a method called a trigger on time. So basically, this is like a helper method that we have in our game for a lot of different situations. For things that have timers on them, you sometimes want to fire some kind of behavior only at a specific timestamp, and then you don't want it to fire after that. So we use trigger on time for that. It just takes the starting time value and it adds the delta. And if it crosses a value, then you fire the behavior. So if the shake, when we pass the trigger time value, then we reduce the intensity of the shaking. That's what the shake damping does. And we update the offset value. Then, if the offset shake length is too short, then we say, okay, we're done shaking. It's not moving that much anymore. So we remove the shake component from that entity. Now it's not going to be processed anymore. It's not going to shake. Otherwise, we're going to update the shake value with the new stuff that we computed. And so that's how we do sprite shaking in our game. That's the whole thing. Everything that shakes uses this exact same code, and we don't have to do anything else with it. Any questions so far? Okay.
Okay.
Oh yeah, of course.
Which is how does the timing work for when the shake component is removed?
It's not timing, so if you look at this line, this if right here,
Yep.
so we're taking the magnitude of the shake basically, and if it's below 1/8, then we're just gonna take the shake component
I
off,
see.
and now it's gonna stop shaking.
Damp at the time intervals, and then when it stands below 1/8.
Exactly. Yeah, oh sorry, I forgot to mention, we're using fixed point math in our game because floats are not accurate across platform. So the fig64 from fraction is basically a 1/8 value in fixed point numbers. Yeah.
Are most of these orange things global?
They kind of. So they're methods that live on a system. So that's why they're highlighted. It's because that is a method that's accessible from the system. So systems can get components from entities. They can set entities. They can set components on entities. They can remove. So yeah, that's what those are.
That sum is a filter? Or at the top?
Oh, sum is like if some component exists at all anywhere in the world. So like if a stop action component exists somewhere, we're not going to execute the system. We're just going to return it immediately.
So it is an option?
Yeah.
Some are not?
Yeah, basically. Yeah.
Could you explain the trigger on time again?
Yeah, okay, so you have like when you create a shape component, it's gonna have a time value on it, which starts at 0. It's gonna have a trigger time on it, which is gonna be like every 5 frames or something, right? So what this means is that on that 5th frame, which is the trigger time, then this code inside the if block is gonna execute. So like every 5 frames, it's gonna damp the shaking,
Okay.
and then it's gonna keep going like for like every other 5 frames. It's basically like on a 5-frame interval, it's gonna execute that code, which cuts the offset magnitude. And then once it's small enough, then we take the component off the entity, so it will stop shaking, basically.
Gotcha.
So that's just like a pattern that, it's not like ECS related really, it's just like a timing pattern that we like to use. Yeah. All right. So here's like a case study. So collision. A game is a set of rules for deciding what to do when rectangles touch each other. So it's pretty important. It's like a lot of your game is going to be defined by collision interactions, and it's something that's pretty hard to structure a lot of the time, at least in my experience. So in most games, I would say collision is resolved between types of objects. So you're going to ask, like, what happens when a sword touches a character? Well, the character is going to die, and there's going to be blood particles, yada yada. I don't think that's a very good way to do things because, again, you run into code reuse issues. You run into problems like where do you actually resolve the collision behavior? Everything is very separated. It's hard to reuse. So in ECS, we're not thinking about types of objects. We're thinking about the capabilities that entities have. So the way I like to break this down is things like, okay, like an actor collision component. It could be like can damage, can break, can deflect. These are effects that an entity could have on another entity. There are receiver components. So these are things that can be acted upon by other entities. So can be damaged, can be broken, can be deflected. So if I'm a character, I would have a can be damaged component on myself. And if I'm a sword, I'm going to have a can damage component on myself. So then you can also have response components. That's going to be like what happens when a can damage object overlaps a can be damaged object. Well, then you can have stuff like spawning blood or the character dying, like spawning a dead body, updating the score of the game, stuff like that. So you break it down this way because now you can build collision behavior just by mixing and matching these different component capabilities. So, for example, in our game, like we did this way, when a sword has a can damage component and characters have a can be damaged component, then when I needed to implement spikes, which kill characters when they get touched, all I had to do was add a can damage component to the spikes, and now the same exact thing happens to the characters. So that's like a nice way to structure this stuff, where you can make it very abstract, and you can reuse everything like over and over again. And eventually you find yourself not even really having to write new collision logic because you're just grabbing components off the shelf and sticking them on new entities that you're creating. So we're going to talk about something I call the fruits principle. So in the Gospel of Matthew, it is said,
Let's go!
So Jesus said, "You will know them by their fruits. Are grapes gathered from thorns or figs from thistles?" So I think that's a pretty interesting epistemological statement, actually. Like, you don't really care like what you think something is or like what it's called. Like what you really care is what kind of use you can get out of it and how you interact with it, right? So when we're talking about ECS, we care about what game objects do and how they interact with other game objects. We don't care about their names or like what type they are. So if you're thinking about defining a component called like bullet component or player component, don't do it. Because what you're going to start doing is you're going to start checking those things, and then you basically have an actor model again. So don't do it, or I'm going to be that skeleton. I'm going to point my guns at you, and I'm going to haunt you. You're going to hear me in the back of your mind. Don't do it. So I call this the fruits principle, and it's something I'm always thinking about when we design a new component. I'm like, am I defining this component to be able to know what this is? Because I shouldn't be asking that question. I should be asking the question, what does this thing do? How does it interact with other things? What are its properties? That's what I'm interested in. So yeah, if you start doing this, you're going to end up with actor model again, but more convoluted, and it's going to suck. So on that topic, here are some component design don'ts. Don't put a collection in a component, like a list or a stack or a queue or something. If you have an entity that needs to have like a list of stuff that it's able to refer to, that's what relations are for. So yeah, don't be sticking big collection structures in your components. Use a relation instead. Don't put a complex state machine in a component. If your components are getting really, really, really big with like lots and lots of data on them, that's a red flag. You can usually model something like that with like a set of like different components that get added or removed or manipulated by a system. It's a much better way of structuring things. If your components are getting really, really, really complicated, that gets confusing. It makes it hard to reuse them. So don't do that. Don't use tag components to hint at what the entity is. That's what I was talking about with the fruits principle. Yeah, don't name something like a bullet or a player or whatever. Like you don't care about that stuff. You care about how the entities are interacting with each other. And then finally, don't reference components or specific entities in a component. An entity to component relationship is just that the entity has the component on it. You shouldn't need to stick another entity ID in a component. You shouldn't need to refer to a separate entity in a component or to a separate component. That's what the entity component relations are for, and that's what entity to entity relations are for. So you should never need to do that. So how do we render stuff? Well, a renderer is just a system, except all it does is read stuff out of the game world. It doesn't need to update anything. So another reason that I didn't mention before that I really don't like about encapsulation is that it's a fucking disaster when you're trying to optimize renderers. Renderers love batching. They want you to batch state as much as possible because anytime you have to switch the state on the graphics device, that's slow. So if you, like, so many times when I review people's code, I see stuff like, oh, like my player has a draw method, and my bullet has a draw method, and I'm just calling all of those. No, bad, don't do it. Filters allow natural batching structures to emerge. So if you have a filter, like, oh, give me all of the entities that have these components on them that need to be rendered in a certain way, now I can set the renderer state for all of those components. I can draw all of those components at the same time, and then I can move on to the next set. That's going to be much, much, much more efficient.
How much FPS improvement did we get going into this model?
So our old game on my machine, like, it wouldn't get past like 80 FPS, I think. And when we moved to ECS, it's hitting like 500 like regularly. It's crazy. Like, it's seriously nuts. So that's a big advantage of doing things this way.
Do you know what blocks were there?
What's that?
Do you know what was blocking you in the old way?
I mean, it was basically just like actor model, like, oh, we're just gonna get all of, like, we were just calling individual draw methods on a bunch of stuff, and then the draw methods would set state, so then every time their draw method got called, they would change the renderer state, and that just makes everything really, really slow.
Inefficient gadget.
Yeah, exactly. So on that note, some architectural advantages of doing things this way. So one nice thing is that increasing the amount of different kinds of entities you have in your game world is not going to lead to an exponential explosion in like logic or type complexity. In fact, in practice on our game, the rate at which we're able to design new game objects is accelerating massively over time because we can just reuse components off the shelf. So we're not writing new game logic for many entities. They get to reuse stuff. very easily. So in most games I've worked on, the more things are in your game, the harder and harder it gets to develop because you're figuring out where everything fits in the type tree and like where it's getting called. But with this system, we're not really having that problem. Our feature velocity is just accelerating like crazy as time goes on. Oh, and yeah, that's my next point, which is as you build out components and systems, the odds that you can reuse stuff you already wrote increases greatly. This system is flexible. That's something really nice because I think a lot of games is about defining exceptional rules. So you'll say like, oh, like this kind of object is going to do this, except if this one thing is true, and then it's going to do something else. ECS lets you define that kind of stuff very easily because if something needs to behave exceptionally, you can just put another component on it. And you don't need to change the type of anything. You don't need to worry about if it's getting to be in an inconsistent state internally when you change stuff. You're not having to worry about like type, like exceptional stuff in like type trees. Like you just add a component or you remove a component. One really nice thing about ECS is that checking if a component exists on an entity is very cheap and it carries useful information. So, for example, like I was talking about our shake system where we make sprites shake if they have a shake component on them. All you have to do is check if that entity has a shake component on it. If it doesn't, you can just ignore that and not update its position in the render. So it's very easy to define little rule exceptions without having to restructure like types or anything like that. There's no hidden behavior. Everything is out and open. Any system can touch any entity, it can touch any component, it can touch any relation. So you're never going to be in a situation where you're like, oh, like, I don't know, the other day I was like, on our music system, I was debugging this problem for like 5 hours because I forgot that, if you have a tree of like parent-child objects, if you, their constructors run in order from parent to child, and I was setting a property in the child object that the parent depended on in the constructor. So I was creating a zero-length array, which like crashed the entire program, and I couldn't figure out why. And it's because there was hidden behavior that I forgot about. So I really don't like that about actor model, and I really like that about ECS. If you like, go in your editor and you're like, find me all of the position component references. They're all going to be there. You're going to see them all. You're going to know where everything is being manipulated, and that's really nice. ECS is very amenable to hot reload. So hot reload is a new feature in C# that we've been using, and what it means is that you can change the code of your game while it's running, and then it'll reload that block of code, and then your game will continue running. So we've been using that a lot for like visual tweaks and stuff because you don't have to shut the game down, change the code, and then reopen it. You can just keep going. The reason you can do that is because there are rules about things that can and can't be hot reloaded. So if your type definition changes, like if you add like a new method where you change the method signature, or you added some new data to your type, you can't hot reload that. Like it won't know what to do. But because ECS, we're not defining types in like the programming language sense, you're just adding or removing components. It's just like a list of references. So because of that, you can change how entities are built without actually modifying anything's type. So we can just hot reload everything in the game very reliably, and that is increasing our ability to debug and add new features exponentially. And I want to do a demonstration of that, actually. Good performance. I want to talk a little bit about this because when you hear about ECS, like the number one thing you're going to hear is like how performant it is and how it can run in parallel really nicely and all of that stuff. Performance is important. I'm not going to disagree with that. I think things performing well is very good. I don't think it's the most important thing about ECS. If ECS was 10 times slower than the inheritance model, I would still use it because it makes designing so much easier. So yeah, you're going to hear a lot about how performant ECS is. I don't care about that nearly as much as I care about how much easier it makes to implement a game. It's memory efficient. Component storage is just a bunch of arrays. Every position component in the entire game lives in the same continuous array, for example. So because of that, you don't need to do annoying patterns like object pooling. Like, if you've used Unity or like other C# game engines, like you probably find yourself in the situation where you're like, why is my game stuttering every 5 seconds? It's because of the garbage collector. So then you have to do stuff like, okay, well, I'll just create 20 player objects or whatever, and I'll just cycle through them whenever I need a new one instead of letting it get reclaimed by the garbage collector. But that's really annoying, and it's really easy to end up in situations where like you forgot about the state on something before it was like gotten back out of the pool or something. I find that stuff really annoying. I've had to write like 20 million object poolers. It sucks. With ECS, we don't need to do that because that's not how it's implemented. Everything is just continuous arrays, and you don't even have to think about it because you're not interacting with that stuff directly. If you're adding a new component or removing a component, you can know that it's not going to make big changes to the memory structure of your game. Natural emergent behavior. So because systems are implemented as like singular logical rules that execute in order, like if you design everything if you design your entities and your systems and your components flexibly, that means that the systems are going to interact with each other logically in like a natural way, and you're not going to have to worry about implementing that kind of behavior manually, which leads to really nice little emergent things happening. And we have easy to build in-game debug tools. So because you can modify the structure of an entity very easily at runtime, like you can make debug tools that just manipulate everything directly in memory, and you can debug things really nicely that way. Some disadvantages of ECS. There's a learning curve. I know, it's a lot to take in, and you're basically turning everything you know about programming upside down if you're used to designing things using inheritance. It's completely backwards. It took me a long time to understand these patterns. And it takes some time to get off the ground. When you start out, you have nothing, and you're like, okay, I'm gonna design my little motion systems and I'm writing my components and whatever. It takes some time to get going. But in my opinion, it's a small price to pay for having much more manageable complexity later on into your project when, it maybe feels like a little bit of boilerplate when you have 5 different kinds of entities in your game projects, but what happens when you have 300? It basically has the same level of complexity, so it's very easy to think about. And there's a saying among programmers that you have to go slow to go fast. I think that's true. It's tortoise and the hare parable. If you're moving really, really quickly at the beginning of your project, but you're making a mess, it's going to be very hard later on, and you're going to burn out. And I think ECS is a very nice pattern for preventing that. Other than that, that's kind of it. I can't really think of a lot of disadvantages of this architecture. I'm never going to go back. It's been fantastic. I think Bo will attest to that too.
Okay. After I was ECS pilled by Evan, back to GameMaker and hated it, and then ended up building an ECS system in GameMaker as we made the rest of the new characters in Samurai Gunn, because I just could not get out of the mindset, because I'm like, it's just better.
Yeah.
There you go.
Yeah.
And now I can't work at anything else.
Yeah, I mean, maybe that's a disadvantage. You're gonna have to go back.
I don't know.
Yeah, Evan ruined my life. I'm unemployable now. 'Cause I
Yeah.
can't get anything else.
Yeah, so I wanted to demo our game actually, so let's do that now. And we can show you some of the stuff in action.
You believe that automated testing? Because this seems intrinsically
Not really.
Oh no.
Oh yeah, I don't got no Thunderbolt, so.
Yeah, it's gonna be pretty hard to see.
Just
on
to
that.
keep-
Yeah, we
You only have one input, one output on your laptop.
Yeah.
what's that?
Don't know.
No. Okay.
Oh, maybe that is Thunderbolt actually. I don't know my own dang computer. Let's try.
17 different input formats.
Oh,
Is that
I'm
it?
gonna say it's a no.
No, no.
Hey!
Oh.
That was the quickest I've ever seen it happen.
Yep.
so we wouldn't say it doesn't work.
I mean, do you want to get this here?
Oh yeah, the code. Yeah, we should
Yeah.
have the code.
Yeah.
Okay.
Okay. Plug it in. This is our game. It's called Samurai Gunn 2.
Hell yeah. Buy Samurai Gunn 2 on Steam.
Yes, it's available in early access.
Available now, early access.
I'm just gonna load our level here. Right, so this is our game. Run around, jump, kill stuff.
Oh, there's the screen freeze effect.
Yes, that's
Yeah.
the screen freeze effect. And yeah, maybe I can show off the shake actually, if I remember how to control this on the keyboard.
Yeah.
If you want to talk, I can jump around.
I mean, yeah, why don't you do that actually? Yeah. See when you hit the ground, shakes back and forth for a little bit. Hits the ground, shakes back and forth for like a few frames. That's the shake system I showed you.
Here, I'll do run at 25%.
Yes, that's a good idea. So yeah, here's time dilation in action.
That way, hang on.
There it goes.
And we also have frame by frame tools.
Yes, so you can step through one frame at a time and you can really look at animation stuff that way.
Just like we have all these test cases.
Yep. Testing characters bouncing off of each other, testing what happens when two swords hit each other in different angles.
So 4 hours a day, I just like do this. And then I'm like,
Yeah. So one thing that's really nice about this, how this works, is so you were asking about automated testing. We don't really have that. We do anytime we're testing a new feature, we build out like a little button for it in our debug editor, and because everything is so decoupled, we just have to spawn entities and components in a certain configuration, and we can recreate the behavior of these actions in our game very easily.
So when you make all of those debug buttons, do
Yeah.
you just put components onto it, or do you have to basically position them at this like on screen?
Well, the positioning is also a component.
Okay.
So yeah, it is just like you just set up an entity. Oh yeah, here's the code. I don't know what's a good example.
run at 1% speed.
Are you gonna add a new thing right now?
Yeah.
So Bo's adding a new function to our game in real time without reloading the project. So
Should be here somewhere.
should be here in like a
There it
second.
is.
There it is. Yeah. So now we can run the game at 1% speed. And we did not have to reboot the game. It's going to be really slow. In fact, I did.
Yeah, it works.
Oh, it does? Oh, is it moving?
I don't know.
It's being rounded down to
That's
the.
F7.
Yeah, right.
Oh, wait.
How integer math do
There we go.
Yeah, there you go.
1% speed.
Oh, yeah.
Look at that. And that did not exist when we started running the game.
And now it no longer exists.
Yes, so now it's gone. Goodbye.
It's super easy when you say speed.
Now it's gone. So that's hot reload. It's really nice. Years ahead. And logs don't bleed because we did not use inheritance. What's a good example? Oh yeah, here's another one we could do. If you go to where the fire traps spawn in the motion system and we change how long they exist for. Flame trap.
Oh yeah, fuck fire. Through the fire and flames. Alright, here we go. So here's as it is now.
So when this character shoots a bullet, it spawns a fire trap that lives on the wall for like 5 seconds. So what if we're like, you know what, that's a little too long. Let's,
Oh, too long.
or maybe it's a little too short. Let's make it last for 500 seconds instead. There it goes.
Make her more powerful. I don't know.
There they are. So yeah, again, we did not have to reload the game to test that. We can just do it.
You also have the
What's that?
code. You also have the code.
Sure, yeah.
Oh, sorry.
I mean, you want to let's look at the flame trap spawning system, actually, because that's a good example of like how empty is put together.
That's kind of related to my question. The one thing I feel like I'm stuck understanding
Yeah.
is if we're not supposed to call things by objects like bullet, right? But you want to spawn a bullet after something happens, like what do you call?
Yeah, it's fine to, like, usually what we do is we have like a method called like spawn bullet or something, or like a message called like spawn bullet message, and then another system actually handles creating the entity. It's just that you're not defining a component that tells you that it's a bullet. So here's an example.
I see, so you
Don't
can
know how to
have
zoom in.
a bullet entity filled with components, but you're not creating a bullet with the behavior. So you can have this bullet entity with just the components and that's it, and then you just call that entity.
Yep. Yeah, because all you care about is like what the bullet is doing, right? So what we care about with the bullet is like, well, it's going to move at a certain speed every frame, and when it touches a character, it's going to kill the character, and when it touches a wall, it's going to disappear. That's the stuff that you care about. You don't care that it's a bullet. Like that's the first
Yes.
principle.
Yeah. So this is
Here's where the bullets are created.
Okay.
You're gonna rename it.
yeah. So it doesn't matter.
So it doesn't matter what it's called. Yeah, so we create the entity and we're going to put the sprite animation on it, the bullet animation. The bullet can be swallowed. One of our characters has an ability where they can swallow bullets, so they can be swallowed. Bullets block spawns, so we don't want characters to spawn right in front of a bullet and die instantly. So we block them from spawning if there's a bullet at that location. So that's a can block spawn component. Control plus, maybe? Yeah, there you go.
Thank you.
I have a question about the data structure of the component. So I'm wondering about, I think earlier on you showed like a algorithm called sum, where you check what for the existence of.
Yeah,
Are those lookups expensive, or how are they?
very cheap.
Okay, and so what's the not the memory level, but I guess at the like compiler level, what's the
The data structure?
Structure, yeah.
It's basically a set of dictionaries and arrays.
Oh, okay, I see. Okay.
And basically there's like, for each component has like a storage array, basically. So every one of that component that exists in the world lives in this one array. And then entity IDs will point to a location in the array.
Oh, I
So
see.
if you have entity 2, and entity 2 has a position, entity 2 will be related to an array index in
I see.
the position area.
Okay,
Yeah.
so structurally, you have so structurally the entities are just dictionaries of indexes.
Entities are just IDs.
Oh, okay.
The lookup dictionary is inside of the component storage object, basically, so that maintains a lookup list of entity IDs to component indexes of
Oh,
the
I see.
component array.
Okay.
Yeah. So the entity has no data on it. It's completely empty except for an ID.
Cool.
Yeah.
You're pulling those filters already?
No, filters are different. Filters are sets of entities that satisfy certain criteria. So the filter will have a list of entity IDs on it, basically. And then when components are added or removed from entities, those filters that are relevant to that component type are going to check if the entity satisfies that criteria and add or remove it from the list.
Okay, so filters have computation.
Yeah, they do. Yeah.
How do you, how do you usually organize all the different components like in a folder?
They're literally all in one
In
giant
one
directory.
Maybe you search for them anyway, so.
Yeah, like in your IDE, you can just look up like position component, so I don't think the folder structure really matters that much.
I see, I see.
Yeah,
Yeah.
yeah, there it is.
Control that.
That's
Yeah,
a fun idea.
okay.
We can add gravity
To a bullet?
Tiles bullet. So right now to go
Okay,
forward.
yeah.
Here's the bullet creation. Set new ball force.
All right, the bullets now have 100 gravity. Let's reload.
Yeah.
It's gonna take a while.
Right, this is a huge script.
Yeah, so one problem with hot reload is that the bigger your method is that's recompiling, the longer it takes to hot reload. So if you have smaller methods, they'll reload like instantly. But this is one giant method that does all the character controlling, so it takes a really long time to recompile. Like we can go through the rest of the components on the bullet.
Oh,
Go ahead.
I was gonna ask, do you ever run into conflicts between different components? Because it seems like we have like 100 components in the file.
There's a lot of components, but because they're all like pretty focused, you just never repeat behavior. And like, you know your game best, so you're gonna know what's missing. And while at the beginning it felt kind of difficult to create like a component or an entity from scratch, you very quickly go like, oh well, I want it to, you know, have a position. It doesn't move, so I don't need to add velocity. I want to render it. It's rendered on this layer, so it's like you kind of end up just developing like a, you know, process.
Yeah, I guess when I'm designing an entity, the question I always ask myself is, oh, there it is. Yeah, now bullets have force on them. All he did was add one line of code. That's it. One line of code. So when I'm designing an entity, the question I ask myself is like, what does this thing do? And then from there, you can break that down into like a component design process. So like again, with like a bullet, you're like, well, what does a bullet do? It moves every frame at a consistent velocity. When it touches things, it kills them. When it touches a wall, it goes away.
Let's spawn a new entity when you shoot. So, well, I won't use the same name. Let's see. So we want it to have a position. Transform 2D. Assuming we have this.
Yeah.
Where is this one?
Is it no position?
Transform that position.
All right.
Oh, I'll take it.
Advanced.
No, I'm the problem. Okay, so now it has a position, so now this is just invisible, but it's right where you shot it. So we want it to be visible, draw as gameplay effect. Doesn't have a sprite though, so that's gonna crash. So we say set new sprite animation. Content sprites dot manga. Let's do it. It's gonna crash because gameplay effect needs a depth. Of course, this is all stuff you can build in the engine, so it's like we just throw an exception because we're like, fix it.
Yeah, exactly.
But it's all up to you.
Wait, so when you say it crashes, does it mean somewhere there's a script that depends on multiple?
Yeah, it's making an assumption, like, it's just like I was lazy. So when I'm like drawing gameplay effects, I'm not checking all of, like, if I was not lazy, then I would put on the filter, like, okay, everything that's a gameplay effect needs to have this set of components that it depends on. There it is.
There it is. Yeah.
So if I was not lazy, I would not have done that, but I was lazy.
So the system that's operating on entity or the gameplay effects components is assuming the presence of a sprite animation.
Yes, exactly.
And you're just gonna get it normal.
And yeah, it'll just crash because we don't have that right now.
So here's our renderer. This is a gameplay effect filter. So we create the filter, and then we iterate through. Oh, that's what pals on. I don't want that.
There we go.
There we go. Okay, so now we iterate through every entity in the filter. If it has flicker, then its visibility is turning on and off. Here's the depth call. So if I didn't want it to crash, I would just say if has depth.
Yeah,
Then
we could set a default or something, but I didn't do that.
Yeah. See here, it optionally takes color blend.
Yeah.
And just returns white if you don't have it. Here's trusty shake. Yeah, we're just like affecting the data and then batching the sprites, and that's it. The rest is snowflakes.
Yeah, so that's the whole block of render code right there. That's rendering that block of code is rendering every single gameplay effect in the game. Like
There's Among Us.
Yeah, there's Among Us.
So one thing,
These are shaders.
Yeah.
So
if they're gonna survive
Yeah, we
in
didn't
every level because I didn't add a destroy on unload.
So those are there forever now.
Yeah.
We should show off the enemy search feature too.
Oh yeah. Really trying to draw a smile. All right.
is your entire UI system also in ECS?
The UI, so this UI is called a Dear MGUI. It's the best thing ever created. Please put it in your game. Yeah, it's incredible.
What's it called?
Dear MGUI, which is short for immediate
Mode.
GUI. Yeah, it's like so it's a style of doing UI rendering called immediate mode, which is I don't know. I don't feel like explaining it right now.
You'll just draw every frame.
Yeah, that's literally what it is. Yeah, it's just like it erases the whole screen every frame, and it's just reading like commands every frame to build the UI. So it's very flexible and it's very easy to integrate into your game because you don't have to build any like long-term state to keep track of.
So you're not using,
Oh my god.
but like the UI, like the data structures behind it, I mean, like are you still using ECS for like spawning the MGUI?
Yes.
All right.
No. The UI is running on a completely separate renderer system, basically, and we actually don't even compile it in release builds. So this UI will only show up in debug.
Oh,
builds.
I didn't mean this UI. I meant your game's.
Oh, the game UI. Oh, the game UI is in ECS.
Yeah.
Okay.
Sorry about that.
How do you spell Dear MGUI?
DEAR space INGUI.
I found that doing UI in ECS makes UIs much easier to program.
Yeah, it does make
That's a huge
UI.
benefit because UIs are the worst thing in the universe.
Terrible.
That is, I will fight you.
So what Bo was doing there was manipulating the state of a particular component.
Yeah. So here's our entity search.
Yeah.
I could look for any draw as gameplay effect. Or wait, you know what's more? We can scale up the character maybe. Once I can set it different. Right? Draw as gameplay effect. So now here's a big list.
It was all of the enemies that have that component on them in the entire game.
I can randomly pick one, and then I can start editing values. This is also stuff it's up to us to build what components are editable.
Yeah.
And then, let me just rotate it 90, I see them. Of course, this is radians, which I don't know as well. Yeah, stretch that boy out.
There it is.
Where is color? Oh, we're getting something, an adjacent texture.
Oh yeah, because alright. Yeah, so you can edit stuff while the game is running using this UI. It's very flexible.
Yeah. Anything else you want to show?
Oh, to answer your earlier question about how we check if some component exists in the world, the way it's working internally is that we know how many components of a type exist in the world on their storage structure. So you can it's basically just checking like how many of these components do I have right now. So if it's greater than 0, then you know at least one exists. Yeah.
Cool.
Well,
So it's just count down the component, right?
yeah, exactly.
There's definitely a lot of principles of functional programming going on here.
Yeah, I think, I'm sure someone has built a functional ECS system. I don't know if I would want to use it, but you can do that, yeah.
Yeah, it seems like all the good parts, but you still get to write procedural code.
Yeah, that's kind of what so this library we're using is one that I wrote. It's called MoonTools ECS, and
It rules.
thank you. Cass is a big fan, yeah.
I've used a bunch of ECS, it's the best one by a huge margin.
So like I designed this very deliberately to be easy to use. I don't think a lot of ECS systems are designed that way. I think a lot of ECS systems are designed with performance in mind, and that makes them harder to use. And I decided to err on the side of easy use. So, I mean, at least as far as I'm aware, this is probably the slowest ECS implementation that's ever been written, and our game still runs at 500 FPS, so I don't really give a shit. Yeah, that's it. If anybody has any more questions, yeah, go ahead.
Yeah, thank you. I feel like ECS has been explained to me about 3 times, and this is the 3rd time where it's actually made some sense. I'm curious to know, what are the implications of ECS moving forward? Do you think there will be a shift from object-oriented programming to ECS, particularly in game development in the future?
I'm really cynical, so I'm going to say no, because programmers hate learning things, especially game designers. It's been like pulling teeth to get anyone to not use Unity for like the last 5 years, even though everyone who's shipped something with it ends up hating it by the end, but everyone still uses it. So I think like it's going to take like a pretty big mentality shift of people being willing, because you have to be willing to invest the time up front to like learn how this works and how to build stuff this way. And I think people really just want to do things as fast as possible with the things they already know how to use. So that's my cynical perspective. If I, was like the dictator of programming, I would definitely force everyone to do things this way.
Elect Evan, dictator of
but I'm not. So, I'm like, this is like my personal hobby horse. Like, I'm really trying to get people to think about programming this way because I really like to do it this way, and I think it's been really helpful for us in production, but like, I can't force people to learn how to do things a different way. But I'm happy to help.
It was challenging, I'll admit it.
Yeah.
And I'd be like, but it's a rock. It's not a wall that can't collide, that can't do whatever. It hurt my brain, and I would never go back.
Yeah.
So it takes a while, but once it clicks, it's like, no, this is it. This is how a game should be made.
And also, like you, I had ECS explained to me several times, and it never made sense until I just tried to make games that way on my own for like a while. And like, it took a while to hit on all these like design principles, and like it took a lot of false starts. And I guess I see my mission as like preventing everyone else from having to go through that much like learning pain to learn this, because I don't think it's really that complicated once you're used to it and if it's explained properly. but I think a big gap is just people don't explain it very well.
Yeah. I was also really, really resistant when we started explaining and pitching it, but I got really into it, and I think the biggest shift in my mindset was like going from valuing getting something on screen that looked like a video game as fast as possible to valuing myself in the future not being miserable.
Yeah, definitely. That's very true. That's my perspective as well. And like, especially because like, I mean, Bo and I have between us shipped several games, and every single one of them has been a unique nightmare to finish. And you know, especially after I shipped, like, I worked on a game called Forager like 5 years ago, and you wouldn't know because they took my name out of the credits, but but that game was such a mess, and that was when I really started looking into ECS actually, because I was like, how can I make sure something like this never happens to me again? So I think there's a perspective shift that you get when you start actually shipping finished products, because you're really thinking about like, how can I polish this, and how can I make sure that it's functional and maintainable long term? And like, that's the question that this architecture solves for me.
Was it Overwatch's ECS?
Yeah, Overwatch uses ECS. I mean, none of us will ever get to look at it because it's proprietary Blizzard, but
There
yeah.
was a GDC talk about Overwatch's ECS system.
Did they talk about it?
Yeah, it's on YouTube.
Oh, well, there you go. Okay.
Like, legal license?
I doubt it.
That'd be smart if it did.
Yeah. Oh yeah, look, there it is. Overwatch gameplay architecture and netcode. Oh yeah, something else I forgot to mention is that our big motivation for rewriting, because the original version of this game did not use ECS, it was made in GameMaker, and we needed to add rollback netcode, which would have involved re-architecting the entire game anyway, so we just decided to re-architect it in ECS instead. And like, there's our rollback component.
It's just like the gamers say.
Yeah, just add rollback.
Checkbox that says rollback.
So yeah, because of how the gameplay state is represented in ECS, it's a lot easier to implement like weird, like state rollback structures like rollback netcode than if we were doing like actor model stuff. Like where the serialization process would be way more complicated.
What was that experience like? Because like, if you're let's say you're in flight game and you want to derive the benefit, you want to balance deriving the benefit from better architecture with the
Production
potential
penalties.
save of
Yeah.
spending a year rewriting the game.
Yes.
Like, what was the experience like of re-architecting the game? What aspects do you think were the most impactful?
Yeah, so I mean, at least like the process of re-architecting this game in particular was, this was my like 5th time like writing an ECS project. It's just my first time writing one for like a commercial project, and so I think that made things a lot easier because I already had, I already knew like how I would do it basically. And I mean, one way that we did kind of start doing that is like after I showed Bo how ECS worked, like he started incorporating ECS elements into the original game, which is something that you can do. Like, if you don't want to rewrite everything, you can start bolting ECS ideas like into your more traditionally structured game, and that will mostly work. I think, like it was time to just rewrite this game from the ground up for us. Like it was based on code that Bo wrote in like 2010, like really old. It was really crusty. There was a lot of stuff in there that didn't work or like was not being used, or like it was just time to kind of redo everything. And I'm not going to say it didn't take a long time because it does, but I don't think we've ever regretted it.
No.
Yeah.
We're committed to the project long term.
Right.
And if you're planning on working on something for like, the next 5 years, continuing to add content, you want it to be like a live service game, it's like the foundation needs to be really solid.
Yeah, so that was our main concern.
So I was feeling it crumble.
Yeah, it was falling apart.
Yeah.
Like by the time we added like several new characters and like levels and stuff, every time we had to add something, it was like, oh god, it'd be like a month of like bug fixing for everything we added.
Did you see the frame rate like start to dip?
Yeah.
Just like,
Yeah, it was so like just like with the reality of like what we want escape to be. Like, we just had to change it. But like, yeah, I'm not saying like go out and like delete your game that you're making right now and like start using this immediately. Like, but you know, just have it in the back of your mind. You know, and maybe on the next project, you know, try it or something. Yeah.
I think the greatest pitch that I experienced for ECS was something that is inaccessible to everybody in this room, for most people in this room, and it was knowing Evan 4 years ago.
Yeah.
I knew Evan when he was working on Forager. I was there working on the game version of Samurai Gunn, and you were just a happier person now. You were just a more, like the way celebrities talk about transcendental meditation, that's how you do with ECS.
It's true. I was miserable. Like staring at like object trees for like 80 hours a week was actually making me insane. So like, yeah, do it for your mental health. Honestly.
Self-care.
Yeah, exactly.
ECS is self-care.
That's my new pitch. Yeah.
But the way it's usually explained is the opposite of self-care.
Yeah, I mean, I agree. And I mean, on that note, like I have a Discord. I'm like one of the co-maintainers of FNA, which is like a free game engine, and like I'm always hanging out in there. And we have a Discord channel for this tool in particular. Come on by. I'll answer all of your questions. I don't care how dumb they are. I will help you. And there are a lot of people in there that understand it now, and sometimes I don't even have to explain stuff. So that's great.
The thing I found in my experience with systems like this that breaks down is when someone likes it, but misunderstands one of the fundamental rules, like don't, like you said you can calculate things.
Oh yeah.
But like, you know, and if you know your C++, that basically means use const. You can only const things.
Yeah, basically. Yeah, you're making everything immutable.
But like, if someone has a bad understanding of that fundamental rule, they'll make a mistake and then run with it, and they'll start degrading.
And then it's, you know, 50,000 lines of code in, and you're like, oh. I mean, that happened to me a lot of times when I was like learning ECS. I'd be like, oh, I completely misunderstood like how this one thing works.
Yeah.
I re-architected a lot of things.
We're seeing a lot of your trial and error and learning.
Yeah, it was a lot of that. And I want to spare other people from having to do that if I can.
Evan is so nice. He took so much time out of his week this week to help me get a deferred renderer working. He's just the best dude.
I'll answer all of your renderer questions too. Yeah, it doesn't even have to be about ECS.
What is the project you're most excited for that's using new tools that you're not working on?
Oh, we really want to make a series of shmups, actually. Actually, yeah, somebody in my channel is making a cool, yeah, you can look at the footage, actually. It's an ECS channel on the left.
Seems uniquely suited for shooters.
It's very nice, yeah, because I'm just thinking about like designing like a bullet pattern editor, and like, it is something somebody who doesn't know me in person is making with my ECS.
This looks fun.
It does look fun,
Yeah.
actually. Oh, wow. Yeah, this was a guy who did not know how to use ECS like 4 months ago. So yeah, people are making some cool stuff. Yeah, we want to make a shmup series. We feel like that architecture is uniquely suited for like arcade style games where you're just composing a lot of pretty simple behaviors together. And like, we're like, oh yeah, if we get this down, we can just pump out like 5 of these in like 18 months, you know, and I think that would be fun, yeah. I'm just looking forward to being able to do things quickly again, because, you know, we've just been rewriting like a giant project right now, and like every month we underestimate how giant it is, and it'll be nice to build something from scratch again, yeah.
I could even see this being very useful for implementing something like Magic the Gathering, where like,
I think it's good for everything.
Yeah, I can't.
Are you making a video game? Use ECS.
Yeah,
Like,
I
honestly,
can't think of a kind of game that this doesn't work for, and you know, I'm constantly surprised at how simple things end up being.
Because even that mindset like changed, rock my world, where it's like data, and then you're manipulating data. That's it.
Yeah,
And like really putting a hard line between them, like just improved everything I built.
yeah.
there's been a lot of focus on action games, but this ECS is really, really nice for complicated narrative games. I've been building a lot of stuff related to like trait systems and like non-branching like salience-based narrative stuff and all of that kind of stuff that like narrative designers love to geek out about. It's so nice in ECS. It's so good.
Yeah, I saw your like relation. Actually, like you wrote like a blog post about your relation system.
Like relational trait system that I got working in like a day with ECS, and it's so nice and so flexible, and it's amazing. It's really, really good if you want to do anything like Crusader Kings, that kind of thing, like big ups to ECS.
Yeah. Yeah, make your games ECS. It's really fun. I'm having a great time.
I'm happier as well.
Yeah, I
My
love my
life
job now.
Visibly improved. And then Hobby Load came along.
Oh god, yeah. If you can start using Hobby Load, do it. It's crazy. it's like nothing else.
That's a Visual Studio feature.
Yeah, it's a .NET feature, and I think C++ can do it too. It's just reloading your code at runtime. It's amazing. You can do anything. That's all I got.